In 1905, a young patent clerk published a paper proving that light behaves like particles. That paper became one of the cornerstones of quantum physics and earned its author a Nobel Prize. The patent clerk was Albert Einstein. But Einstein's relationship with quantum mechanics didn't end there. That's exactly where it fell apart. As quantum mechanics developed, a deeply uncomfortable picture emerged. When you observe an electron, you find it in a specific spot. But before you look, that electron isn't in any definite location. It exists everywhere at once, like a cloud of probabilities. The moment you observe it, the cloud collapses and the electron shows up at a single point. Sounds ridiculous, right? Einstein thought so too. In a letter, he wrote, "I refuse to believe that God plays dice." That wasn't poetic language, it was a direct protest. Einstein's argument was straightforward. Physics should describe events with certainty. If we can't pinpoint a particle's position, that's our instruments falling short, not nature itself. There had to be hidden variables we hadn't discovered yet, and once we found them, quantum mechanics' probability-based interpretation would dissolve. A Danish physicist named Bohr stood on the opposite end. Uncertainty wasn't a flaw, it was how the universe operated. Period. The clash between them turned into one of the fiercest intellectual brawls in physics. Einstein kept designing thought experiments to tear quantum mechanics apart, and Bohr kept finding the gaps in those experiments and shutting them down. The hardest punch landed in 1935. Einstein and two colleagues published a famous paradox that shook the foundations of quantum theory. Their claim was this: the instant correlation between two entangled particles proved quantum mechanics was incomplete. Information couldn't travel faster than light, and this spooky action at a distance defied the rules of physics. For 30 years, the debate hung in the air unresolved. Then, in 1964, a physicist named John Bell changed the equation. Bell showed that Einstein's hidden variable hypothesis produced testable mathematical limits. If hidden variables truly existed, experimental results would stay below a certain threshold. If quantum mechanics was right, that threshold would be crossed. In 1982, a French physicist ran the experiment. The threshold was crossed. Nature operated in ways far stranger than Einstein was willing to accept. But here's where the story gets really interesting. Through the very argument he lost, Einstein unknowingly laid the groundwork for a technological revolution. That same paradox triggered deep research into quantum entanglement. Today, quantum computers use entanglement to tackle problems that traditional computers would need hundreds of years to solve. Quantum encryption creates communication channels that are mathematically impossible to crack. Quantum teleportation experiments have successfully transferred information without any physical carrier. All of it was built on the entanglement that Einstein called nonsense. So why did Einstein resist so hard? It wasn't just about the physics. Einstein was committed to determinism, the idea that the universe runs on precise, predictable rules. The need to see the universe as orderly and meaningful is what led him to relativity. But that same need blocked him from accepting quantum reality. The mindset that carries a scientist to the top can also lock that scientist in place. Einstein didn't miss quantum mechanics. He deliberately rejected it. But the arguments he built against it ended up accelerating its confirmation. If you were to list the most consequential mistakes in the history of science, Einstein's quantum objection would probably sit near the very top.